Hello students, welcome back to another lecture which is lecture number 25 in our classical mechanics. And in the last 2-3 classes we have seen the central force problem, and the main conclusion has been done, namely that the reduction to the one body problem, and we have also written down the Hamilton's equation of motion and the identification of the constants of the motion. So that was the major physics involved there, which means that the symmetries in the system has been identified. And what can be done after that is that you can take down the Hamilton's equation of motion for the central force problem, and then you can obtain the differential equation of motion. Okay, that is one thing that you can do. And the second thing is that if you are going to solve the differential equation for a particular case of minus gmm by r, then you can show that the equation happens to be the ellipse when the total energy is less than 0. So these are the two possible exercise that you can do, which doesn't involve much mathematics, as well as there is no physical implications directly coming there in the derivation. So that is the one that can be done. But there is one interesting and important point that I would like to mention before we go on to the today's topic of the rigid body dynamics. Namely that in the central force problem, there is one theorem is there, and the name of the theorem is Bertrand theorem. Okay, and the statement is quite simple, but it is very important. The Bertrand theorem says this: okay, out of the infinitely many central potentials that are possible, there exist only two potentials that are very important. So you understand the meaning, right? You can write down infinitely many potentials mathematically, all of them are central, but out of that many number, only two of them are so special. So what are the two special potential is? The first one is the 1 divided by r potential, that is 1 over r potential. This is the first important potential, that is the one corresponding to the gravitational. The second category of the potential, which is very important, is the harmonic oscillator potential, which is nothing but k times r square. So you get two of the examples, right? One is the 1 over r potential, the other is the k times r square potential. So rather than saying in terms of equation, we can always say that the one corresponding to the gravitational potential and the one corresponding to the harmonic oscillator potential, they take the very special place in the central force problem, because the reason why it takes so importance is that only these two potential generate the closed orbit, because you know how the mass is going to move under that potential. Ultimate conclusion is that only for these two potentials it is possible to obtain closed orbits, which are also bounded. So in all other cases, okay, the moment you are going to deviate from these two potential, you will end up with sometimes bounded potential, but it is not closed orbit. Something like spiral is, it is not closed, but at the same time it is bounded. So spiral orbits are possible, or you can completely go to the hyperbolic and parabolic orbits. So anything is possible. So this is one important theorem. Name of the theorem is Bertrand theorem, and essentially it talks about the stability of the orbit by taking the appropriate derivative of the potential and setting it to equal to 0. So that is one interesting thing about the central potential. And the concluding and important remark I would like to say is that there exists another constant of the motion in the gravitational central force problem, and the name of the conserved quantity, or the name of the constant of the motion, is the Lenz vector, L-E-N-Z. Okay, L-E-N-Z, the Lenz vector. So it is also called a Laplace vector. Sometimes it is called a Laplace-Runge Lenz vector. Okay, these are the names that it is called. And the symbol for the Lenz vector is typically capital A. Okay, that is one more interesting thing, and you can work out on that based on the geometry. So basically it is not easy to discover that constant of the motion, by the way, but several people have discovered after studying the geometry of the Kepler's problem. So that these are the 2 points that I would like to make before making a conclusion and moving to the next topic. So keep a note on that. The first one is the Bertrand theorem. The second one is the Laplace-Runge Lenz vector, which is a constant of the motion represented by the symbol capital A vector. So with that, we will say that we are closing the central force problem. And in today's class, namely the lecture number 25, we are moving to the rigid body dynamics. And the plan here is that we would like to emphasize the fact. What is that you want to emphasize in the rigid body dynamics is that the if you are going to have one rigid body, the number of degrees of freedom is going to be different from what you study in particle mechanics. That's the main thing. First point. If you are going to consider a single particle, if you are going to consider a single particle and then allow it to move in three-dimensional space, then you already know that there are 3 degrees of freedom, x, y, z. But in the case of the rigid body, it is not so. You are going to have additional degrees of freedoms are required. And therefore, what happens is rigid body problem, or we say dynamics of rigid body, by the way, is going to be somewhat complicated than the particle dynamics. This is the first point. Second point is that when the rigid body is going to rotate, then there are additional complexities are entering into picture. In the case of the particle motion, you don't consider the rotation. That's what I used to tell. Many times I have said that whenever we are talking about the particle mechanics, we don't consider the self-rotation of the particle itself, which means something like spinning of particle. Thereby, we don't introduce a term called moment of inertia. Such a concept of the moment of inertia is not there for the particle in particle mechanics. So, in the case of rigid body dynamics, you see that an additional complexity will come because of the moment of inertia. These are the two things. And further, what happens is that when you don't have a proper symmetry in the system, and if you don't have the what you call the uniform density, if the material is not having uniform density, because it's a solid body, right? Rigid body means solid object. If you're going to have a situation where a non-uniform density is there, then automatically what happens is that things are getting complicated and moment of inertia cannot remain as a scalar. That's the conclusion now. I would like to tell right now that moment of inertia can't stay as a scalar quantity, but rather it is going to behave like a tensor quantity. So moment of inertia is a tensor ultimately, as far as rigid body is considered for a general case. If you are going to consider some very symmetric case, and then when you are having an appropriate coordinate system established, then even for the rigid body we can have a scalar. So scalar quantity for the moment of inertia is something special, where you have a high degree of symmetry and also isotropic. When the symmetry is missing, when isotropy is missing, which means anisotropic situation, the moment of inertia is going to be a tensor quantity. And by that, you don't have to be afraid of the terminology tensor. Tensors, by the way, is fairly simple within the limits of the rigid body dynamics, as well as to the limits of the special theory of relativity. So to that extent, the mathematics of the tensor is fairly simple. Unless you want to study something with the general relativity, at that time little more knowledge about the tensor, in the sense tensor calculus like contravariant derivative, covariant derivatives you require. But right now, within the limits of rigid body dynamics and special theory of relativity, the concept of the tensor is going to be quite simple. So there is nothing to worry about, and I will introduce appropriately as we go along. Therefore, right now there is nothing is to be thought of as some complicated item. And for now, let us start with what is the rigid body dynamics, how to deal with the dynamics of rigid body. So the first point let me therefore have is that let us draw a diagram, roughly arbitrary means any shape. We don't have to consider a particular shape for the rigid body. We will consider some arbitrary shape, that is any shape, and we also assume that the density is not uniform. Density is not uniform means you'll have to understand that some part of the rigid body is quite having massy, and some part of the rigid body may be lightweight. Such kind of mixture. You can imagine like this. You can imagine that some wooden powder. You take powder of wood, and you also take the powder of some metal like iron. And if you mix them, and then make a ball. Okay, then how does it look like? Okay, there is no guarantee that the wooden powder will mix homogeneously with the iron powder, and therefore some part of the ball will be lighter, and some other portion where more of the iron powder is there, it will be a little bit heavy. That kind of situation is what you can imagine, and you can see what is the meaning of non-uniform density. Okay, when these kind of situations are coming, we say arbitrary. Arbitrary means any kind of rigid body. So let us therefore proceed, and then let us see what happens if you are going to deal with an appropriate equation. So let me therefore draw a diagram first of all, and here is the rigid body that you have, and I'm not going to give a particular shape, and then let us assume that there is a center of gravity. That is what I am planning to do, and then I'm copying this and rotating it. Same diagram is there, I'm copying and rotating, so that we say that from the starting point and you go to another ending point. That's called dynamics, right? Dynamics means as time changes, it is moving and rotating. So it has moved to a different place, and also it has rotated. COM means, as usual, the center of mass of the rigid body. So the point is clear, whatever I am trying to say, that the rigid body is moving from one place to the another place. When it is moving, it is also rotating. So dynamics means that's what I am trying to write down, that the dynamics means you have a combination of translation and rotation. This is very important. We don't bring this concept in particle mechanics. So I will write down that particular point now. The translation is one of the basic thing that you already know. So I write first translation. I'll say pure means, I think you better understand, pure means you don't mix with rotation. So pure translation plus, I'll write plus, pure rotation. Which means that for our easy understanding, it is better to consider separately and then add them. Then if you study that is called the dynamics. So I'll write down that this is the dynamics of the rigid body. I'll write RB. RB means rigid body. So what is dynamics of rigid body? Quickly you can tell the answer. The dynamics of rigid body consists of the studying the pure translation together with pure rotation. And that's all about it. Okay, so what happens? So I'll write down now translation. You already know how many variables are there, namely the XYZ variables I am talking about, and therefore you have 3 degrees of freedom. So I'll write down that 3 degrees of freedom. Okay, so this is already known to you. Now, what about rotation? So rotation also will give you additional degrees of freedom. They are the angles theta x, theta y, theta z. I think that suffix is not good. I'll delete it. I'll put some other symbol without suffix, something like theta, phi, and then psi. So advantage is you don't have the suffixes. Which means that we need 3 more variables. So I will now write down that this is 3 degrees of freedom. And what I mean to say is theta means it is a rotation with respect to the x-axis, and similarly phi means with respect to the y-axis and z-axis. Okay, so you understand what it is, right? You keep the z-axis, and then with reference to the z-axis you rotate. So we already have the 3 degrees of freedom additionally. So 3 plus 3, I am putting a box now. That gives you 6 degrees of freedom. So the conclusion is clear. I will write down the conclusion therefore. We have 3 plus 3. That is the conclusion I am trying to say right now. And we say that we need 6 degrees of freedom for our problem. So once I finish that, then probably we can move rigid body into 6 degrees of freedom. That's all about it. So this is the main conclusion about the study of the rigid body. This is how you start with. This is the first requirement. And then we will see where is the difficulty coming into the rigid body dynamics that was not there in particle dynamics. So I'll write down that. What is the difficulty in the rigid body dynamics? So as we have summarized, first of all, I'll write down that translation plus then rotation. Okay, that combination is what is called dynamics. That is what is the first mean. And the rotation is the one that is getting complicated. I'll put a box there. Okay, the rotation is the one that is getting complicated. and therefore what happens in the rotation, why it is getting complicated, let us see that. Okay, now the rotation requires the definition of a point. I'll write down each point, whatever I am speaking, I'll try to write down so that it is also easy for you to make notes. Okay, if everything goes in a kind of a statement, then you will have to remember. But if I write something on the board, you can also write down and then make the notes. So rotation requires a point, or we say about a point, and there is also additional concept of rotation about an axis. So the clarity is required. So for that purpose, let me draw a diagram. You understand what I say? Rotation is about a point. Rotation requires an axis of rotation. So if I draw a diagram, you can understand better. So I'll draw a diagram. Of course, this is a particular toy. You already top. This is the toy that you must have been playing during your childhood, and this is actually the spinning top that I am drawing, which will give you where is the fixed point there, and also axis of rotation. So you can get the idea about the axis of rotation as well as the rotation about the point. So both the concepts will be visible if from this diagram. So okay, let me finish this diagram. So now we will search in this diagram. Okay, this is the so-called spinning top diagram. Okay, now we will ask the question, where is the point? About a point. So that is visible now. So now where it is visible, you see the bottom, that's the place. Okay. So the point of rotation is very clear, but about the point is very important. Okay, every time you have to say that the rotation is taking place about. So about is very important. Then you'll have to tell what is the point. In addition, you require an axis. So that is where the complication comes. So I'll also show where is the axis of rotation. Okay, I will draw it in some kind of a pink color. It didn't come properly. I'll draw it again. You'll have to draw properly, straight line you'll have to draw, and a pink color line, fully, that is good. And now you say that is called the axis of rotation. And this particular is only typically, it can be in any direction, it can rotate, but I am typically showing this is how traditionally we show how it is. It can rotate clockwise or anti-clockwise, that is okay, whatever be the case, but we will say that is an axis of rotation. And then we should also put a mathematical symbol omega for the angular velocity. So let me put the omega also. Okay, but I think this is in pink color, let us keep, and omega I will write it in white color. So what the idea is now clear. Where is the rotation about the point, it is clear, and what is the axis of rotation, it is clear. But now the confusion comes. What is the confusion is that now we are going to drawing the direction of rotation. So I'm talking about the convention. Let us see how to represent the axis of rotation as a vector quantity. So that is a convention you must have learned, but let me make things clear. The axis of rotation is what is the dashed line, and then we say that omega is the angular speed. And the point we noted is omega doesn't have a vector quantity. You see carefully, I did not put a arrow. Okay, so this omega, therefore you will have to equivalently write down as a vector. How to do that? This is how you do. So you put a vector quantity and then you show an arrow like this. The question is, how do you know that is the arrow? Okay, so the rule comes like this. You simply follow you take a screw, right-handed screw, and then if you are going to twist the screw in the clockwise direction, then how the thread will move, that is the direction. So that's what the point is, that you'll have to carefully see that omega doesn't have a vector on top of that. I mean the arrow. Okay, vector is not there. But when you are going to make a translation, translation means convention mathematically, and now we are going to put a vector. So how this kind of thing is clear is from the what you call the right-handed screw rule. You take a screw and then twist the screw in the clockwise direction. Then in which direction the thread will move forward. That is the direction of arrow. So this is very important. If you are going to follow this, then it is the same thing that we are going to follow for the angular velocity. So this concept is it may be quite simple, but this is very important. This is going to decide the plus value and the minus value for the omega. So that is the point to be noted. And therefore, let us see now in mathematically what does it mean. That's what I will now explain that after finishing this. So this is very important. The reason is axis of rotation, when I am saying pink color, that is not a fixed one. That will change. There is a conclusion now. Omega is a function of time. So this concept is crucial, very important. Axis of rotation is not a stationary one. It will keep on changing as time changes. So whatever thing that I have written now important, that I am writing it as a conclusion. Conclusion is mathematically what does it mean? When omega is a function of t, what is that you want to do? So what is that we have to do is mathematically we have to perform derivative. So let me write down that we have to deal with the time derivative of the vector. Because omega is a function of time means we have to perform time derivative. Mathematically we can say vector, any vector. Okay, but now the omega means angular velocity. So even though mathematically we say it's a vector, practically we have to deal with the angular velocity vector. That is the meaning of this. Okay, so mathematically let me write down a general vector capital A. You can always take capital A as omega, right? That can be taken anytime. So our conclusion and important thing is that we need to take the time derivative of a vector where the vector is represented by capital A. So let me write down that. What do you mean by that? A of t means omega of t. You please, in case if it is difficult for you to understand, A of t means omega of t, where omega is angular velocity. So I want to explain what is the meaning of dependence of time. So I am writing both the options. Let me finish the option, then I will explain. Okay, as you can see that magnitude and direction. What I am writing is, it's simple, right? Vector means vector has a magnitude, vector has a angle. That's what I am writing. Only the theta can change or only magnitude can change. There is a third option, right? That I will write down later. The third option is that all the thing can change. So our conclusion is only magnitude can change or only angle can change. These are the two options. Third option is there. Third option is that all or both of them can change together. Okay, so what happens? So what? That is the question. So now we'll write down that. So what is happening? So our conclusion is when both of them changes, our conclusion is the pink color, I said, right? The pink color axis of rotation, that is not at all stationary. That will be a function of time. So the terminology is the instantaneous axis of rotation. So this is a very important terminology. Frequently the terminology is used in the literature of the rigid body dynamics. Therefore, the concept should be clear to you. What is the meaning of instantaneous axis of rotation? Axis of rotation is not a constant. The axis will keep on change as time changes. So let me therefore show a typical illustrative diagram how it is changing. Now this yellow color arrow that I am drawing is typically an axis of rotation, omega. That's what it means. This is stationary. Now, with respect to time, what happens is angle can change, magnitude can change. If it is changing, how it will look like? That's what I am trying to draw now. I am trying to draw if the length of the arrow is changing, if the angle is also changing, then after some time, how it will look like? The answer is that is what it looks like, something like a cone. It is not a cone ultimately, but it will occupy all the places in the cone. That is what I am trying to say. Sometimes here, sometimes this side. So I am now drawing the left side, right? It can come there, or it can go in the middle of that region somewhere. It can go anywhere within that conical region. That is exactly what I am trying to say. So I'm trying to draw 4 different possible places where the vectors can go. Okay, so those arrows, whatever I have drawn, they represent possible places at different times. So let me write down that these are the possible positions or possible axes of the omega vector at different times. I use the word tip here to say that the length of the arrow is changing, isn't it? You can easily observe the length of the arrow is changing, and also the angle is changing. So the concept is that it is an instantaneous axis of rotation. That is very important. Axis of rotation is not constant, and therefore most frequently the terminology used is that the axis of rotation will create a cone. Okay, so the cone generated by the axis of rotation is the terminology in the frequently used in the rigid body dynamics. So now the things should be clear. Otherwise, you should find it difficult. Where is the cone coming into picture here, right? So once this is clear, now we'll move on to a different place in the board, and then let me therefore write down the next topic, namely that what will happen in the case of the translation and rotation with reference to mathematics. Okay, is it a vector or not? Let us see. Okay, the question should be clear to you. I am asking the question whether translation is a vector or rotation is a vector. So that is the question. Let me write down the first part. Translation is vector or not? Agree or not? That is quite simple. You should agree, because you have been doing this for all the way from school. Xi plus yj plus zk. I am talking about that, which is the traditionally R vector. So you know that this is the translation, and therefore you agree that translation is a vector. No doubt about that. Now, as I already told you, that rotation is the one that is going to create some difficulties in rigid body dynamics. So we ask the question, what about rotation? Rotation is vector or not? That is the question. You have to tell yes or no. The answer is not that simple. So we are going to therefore consider the 2-dimensional case as well as in the 3-dimensional case. So let me straight away give the answer first of all, then we will see the discussion. The conclusion is that the answer is not a simple answer. So, but instead we have some situations like 2D you have one answer and 3D you have another answer. Let me write down that splitting. Okay. I mean the two different possibilities I'll write down. So in 3D cases, you have 2 options. I'll write down the 2 options here. The first case is where you can consider finite rotations. So let me write finite rotations. And the second situation is infinitesimal rotations. Terminology I will again explain. Okay. Finite rotation means theta is finite number, 10 degree, 20 degree, 30 degree, etc. These are finite rotation. Okay. And then infinitesimal rotation means very small. Infinitesimal rotation. 0.01, 0.05 degree, 0.1 degree, this kind of small angle, very small angle. Such kind of rotations are known as infinitesimal rotation. So let us see the answer. What is that yes and no? That's what I am trying to say. For infinitesimal rotation, the answer is yes. It's a vector. So I will write down yes here. Yes means yes, it is a vector. That is the meaning of yes. No means no, it is not a vector. Okay. So now you see the complication 2D yes. Okay. And 2D case, it is a yes vector. But in the case of the 3D, you have both the options are there, no and yes is there. And therefore, we will have to understand how this much of complication is there. How do you know this, first of all? I am telling you the answer, right? But you should now ask the question, how I can't understand your statement. We would like to have more explanation. So let us see that now. Okay, so what I am trying to say is that at least for the infinitesimal rotation, we have yes. So we are fortunate enough in this particular case, because we are going to have the definition for the angular velocity omega, which is defined as d theta by dt. right? So I'll write down d theta by dt. And how do you define mathematically d theta by dt? Elementary mathematics, elementary calculus. In the limit of the delta t approaching 0, then delta theta by delta t. That is how you define. This is the definition of the angular velocity. So why this definition is so important now is that you'll have to pay your attention to the delta t approaching 0. What do you mean by that? It's a very small time. In very small time, if you are going to consider a rigid body, how much angle will it rotate? It won't rotate by 100 degree, right? 60 degree, it will not rotate, because you are going to consider very, very small time approaching 0. That is why this is getting now importance. You please see this point should be very clear, that on the left hand side I have a vector, right hand side vector is not there. That is why I am writing some story now, where the vector on the right hand side is to be fixed as per the right hand screw rule. These are the points to be noted. Right hand side vector is not there. See that vector is not there means arrow is not there. Left hand side omega arrow is there. So you ask the question, where the arrow has gone? Arrow didn't go anywhere. You have to determine from the right hand screw rule, and then appropriate unit vector has to be attached. So these are the places where things are going tricky in the case of the rigid body rotation. So the concepts are important. Now I will go to explanation. How do you say 2D rotation is vector? How do you say finite rotation is not vector? And all that. Okay, so let us, I think this board is full. I'll go to different place of the board, and then try to draw some diagram and then explain what is actually happening in this case. Okay, first I will start with the 2D, because that will be somewhat easy to check it out. I'm writing something easy to check. So because it is a 2D case, you can take something like a planar sheet, like a scale. You have scale with like that. You draw some diagram that looks like a scale, and then you can think about rotating. Okay. So anything like that you draw, and then rotate by some finite number. Finite number means 10 degree, 20 degree, 30 degree. It's okay, anything. And then you start rotating. Because it is a planar rotation, already. Simply you rotate in the plane itself. So you don't have to bring it outside the plane. Okay, that is what I mean to say. Any number you put. Now let me choose 10 and 80. Okay, and if you are going to rotate, how this is going to appear? So finally what happened is horizontal scale has become vertical scale, isn't it? If you consider scale as a typical object, you don't have to draw. You can actually take the scale and rotate and check it out. It's very easy. So our conclusion is that if I am going to start with horizontal scale and then rotate by 10 degree, which I will call it as theta 1, and then I will do another rotation by an angle theta 2, then what is the conclusion is that the final configuration is that I'm having 90 degree rotation. Okay, now what I'm trying to do is, let us reverse this. Okay, let us reversing means what? You apply theta 2 first of all, and later you apply the theta 1. That is what I'm trying to say. So if we do that, what will happen? So let us try to do the experiment by drawing it. Take a horizontal scale as usual. So first of all, I will draw the horizontal scale as original. Now what is theta 2? Theta 2 is 80 degree. So write that. Theta 2 equal to 80 degree. Apply that. 80 degree you rotate. Okay, if I rotate, it looks like this. Something like that. 80 degree rotation. So finish the diagram. And then once the diagram is so fine, looking fine, and then can apply now the first angle. First angle is how much? 10 degree. So now you have to rotate 10 degree now. Then I will be getting vertical one. So what is the conclusion is, okay, it comes to vertical, that's clear. Now immediately, now you can write down the conclusion. So This is the final configuration. Configuration means the way in which the scale is going to appear to you. Okay, in the first experiment also you have the same appearance. In the second experiment also same appearance. Experiment means what? Theta 1 first, theta 2 second. In the last experiment, theta 2 first, theta 1 second. So in that order, you have to be careful. What is that we are changing? Order is changing. Our conclusion, let us write down that theta 1 first, then theta 2 second, theta 1 plus theta 2, and equal to theta 2 plus theta 1. That means I can always interchange the order, but remember thetas are vector. So that point you have to remember. Okay, so theta is a vector quantity, and how do you know the angle? How do you know the positive or negative? That is coming from the polar coordinate system, which you already know. I'll write down that where the arrow is coming from the polar coordinate system, 2D polar coordinate system. That means you can simply draw xy axis and one theta, which is familiar to you. But I think better I will draw for clarity. So you take any point there and then connect the one line, and the direct. Now you be careful. You see the arrow there. Now that is the arrow I am talking about. You see the arrow is plus theta or minus theta. That definition is coming from the polar coordinate system. So there is no problem for 2 dimensions. So for 2 dimension, this corkscrew rule, nothing is required. You don't require any screw there. Okay. So our conclusion, let me write down mathematically the same theta 2 plus theta 1 conclusion. I will write down in a general mathematical notation A and B. So let me come here and I will write down the conclusion, that is, okay, that is only if A plus B equal to B plus A. Okay, only if A plus B. Why I am writing A plus B? Because theta is not very important. Mathematically speaking, A and B is a vector. So I am writing like this. If A plus B is equal to B plus A, we say that it is obeying the vector addition rule. Because vector addition rule is something that you already know, and that rule has to satisfy. If that rule is not satisfied, then we cannot call that object as a vector. So you have to realize what we are writing. Okay, so in general, A plus B should be equal to B plus A. Then only you agree that it is a vector. Otherwise you won't agree, right? That is the reason now we are saying that this rule is now obeyed for theta. That is, we say theta 1 plus theta 2 equal to theta 2 plus theta 1. So now you understand how we are giving the connection to the vector algebra and to the angle here. Because of that reason, we agree. That is what I am saying. Either you say agree or accept. Okay, we accept that. What is it you are accepting? We accept that rotations are vectors. That is our conclusion. We accept that rotations are vector. But the rotation is done to something happening. But rotations are done in 2D. That is very important. So let me write down that the rotations in the 2 dimension is a vector. Okay, that in 2 dimension is very important. I will write down that. Yeah, rotations in the 2 dimensions is a vector. So this is the first important conclusion. It is very, very simple and straightforward. Now you will be able to follow the 3-dimensional case. Okay, the reason why I have done 2-dimensional cases, it is easy to grasp the fundamentals, and therefore I better write this. What is that I am writing now 10 degree 18 degree is that I want to explain what is meant by finite rotation. Okay, there is a confusion between finite rotation and infinitesimal rotation, right? So what do you mean by finite number? Is some number like 10 degree 80 degree 60 degree 100 degree. These are the this is what we say the finite rotation. So let me therefore insert the word finite there. Okay, so I will insert it now. That is an insertion. So rather than saying rotation, I will say finite rotation. So what is that infinitesimal rotation? Is just a fraction of a degree. 0.1, 0.1 degree, something like that, 0.01 degree. That kind of numbers, if you are going to take, okay, if that kind of number is what you are going to take, then I will say that they are known as the infinitesimal rotation. Infinitesimal means very, very small. Very, very small. So any number less than 1 degree is okay, practically okay. Less than 1 degree, practically okay. But when you are performing the calculus with the dy by dx condition, you know that the denominator should approach 0. So very small number is satisfied. So in that way, when you are performing calculus operation like angular velocity d omega by dt, infinitesimal rotations are fine. Okay, let us go to the 3D case. That means now you have to draw a similar diagram. I'll go to a different board because this is full now. Finite rotations in 3D, that is the first thing, let us see. Infinitesimal rotation could be easier afterwards. First I will explain the finite rotation in 3D. Okay, so here what happens is now you cannot consider 2D objects. Okay, let us, our drawing should be something, it should look like 3D object. Okay, something like matchbox. I am trying to draw a matchbox kind of object. So if you're having a matchbox with you, you can immediately take it and verify. Drawing diagram is somewhat little time consuming. So let me draw it anyway. Actually, you can perform this experiment, keep the matchbox in your hand and rotate and see. That is quite very fast. You can check it out in 1 minute. But for drawing purpose, it takes a little time. So let me anyway draw it. Okay, that is a kind of a matchbox that you have, and then fix the coordinate system somewhere. Okay, I don't want to fix the coordinate in the middle. Okay, somewhere you fix it. So that would be one of them will be the horizontal one, y-axis, and that will be in x-axis, and then the z-axis vertical. Like that I will draw. So let me now put this. Now that will be the first one is z-axis, then the x-axis, and then the y-axis. Okay, this is the starting configuration. Okay, this is how we are going to start the experiment. So let me write down starting configuration is like that. And then you are now performing the rotation about the different axes. So let us now start with one rotation, namely the rotation about the any axis is okay. Let me write down x-axis. So what experiment we are going to do is we are going to rotate this particular matchbox about the x-axis. That's important. So I'll write down that. So x-axis rotation, where is x-axis is there, you see, and we are going to rotate in a counterclockwise direction. So here also I will draw the counterclockwise rotation so you can see where to rotate. Now we are performing rotation by 90 degree. I think better we will rotate by 90 degree, otherwise it will be complicated. Okay, 23 degree means drawing 23 degree rotation is little difficult. So I will rotate by 90 degree and I will draw. Okay, so this is 90 degree rotation. So how it will look like? Okay, so I will try to draw the best possible diagram. Hopefully this looks like 90 degree rotation in the anti-clockwise direction about the x-axis. Okay, so once you finish that, we will again fix the coordinate system at the right place. Okay, choose the whatever place that where it is supposed to be, you imagine after rotation, and then you can draw the other axis. Axis will remain same, so y will be y, x will be x. That will not change. Okay, x will be x only. Now this is the rotation that we have performed and corresponding to the 90 degree. So let me therefore write down theta 1 equal to 90 degree. Theta 1 I am writing because it is first rotation. Okay, now let us move on to the second rotation. Okay, and the second rotation would be the one corresponding to a different axis. That's all about it. Instead of taking x-axis, you take y-axis now. So that would be the possibly the second rotation that we are talking about. 90 degree we are choosing because easy to draw. If you take 17 degree, 91 degree, it's a little difficult. So let us consider 90 for quick drawing, and then we are going to rotate about the y-axis in the clockwise direction. So the direction should be visible now. If I rotate like that, how it is going to appear? I'll try to draw how it is going to appear. It is going to lie like horizontal, right? Now it is standing up. No, matchbox is standing up. Now it should lie down. That should be the appearance. I try to draw like that now. See, this I am drawing in the stylus pen. Okay, that is not, this is going very smooth and going somewhere. If you have a scale and a pencil, it will be much more faster. You can draw it actually. Okay, hopefully that looks fine. Now let us put the axis now. So where will be the axis? The same origin. I'll try to put the origin. The rest of the thing is okay. So that will be x, y, z. Okay, now the almost drawing is over. Now this is your final configuration. That's what I'm trying to say. So we have performed 2 rotations. Okay, this configuration is what you have to remember. Okay, I got this. Final configuration. How did you get that? Also you have to remember. First theta 1 is 90 degree about x-axis. Second rotation is about y-axis. So over this first experiment over. So let me say that I'll put some line. Okay, maybe if I put a line, then it is clear that this experiment is over. Now we are going to repeat the experiment by changing the order. Okay, so let us close this. Okay, that's all. So I think we will come to the second experiment where the rotation has to be interchanged. The order of rotation will be interchanged now. So I will try to draw in a different color. Okay. So original configuration should be identical. So let me draw the first one. Starting configuration should be identically same as what you started with previously. So whatever is above, that should be, hopefully that should be copied down here. It should look like the same as the original configuration. So once you finish drawing that, you start rotating in the y-axis. So hopefully whatever is there above starting configuration, I am trying to copy now. So once that is clear, I'll draw the x-axis, y-axis also. So that is fine. Now let us apply. And now let us apply the first rotation with this particular starting configuration. So what are you going to apply? Y-axis rotation I am trying to apply, because that was the second one. See this, the theta 2 was there, right? The theta 2 whatever was there, now I am going to put it now with the first place. So that is why I am writing y-axis rotation, and therefore that will be rotated in the same style as you have done earlier in the clockwise direction. So that also I am showing. So if you are going to perform the rotation, then how the configuration will look like. So that I will try to draw. It looks in a horizontal plane. Okay, now the matchbox thing should look in the horizontal plane. So that is the one I am trying to draw. It takes some time, so let us wait until. If you are not careful enough to draw, then appearance will not be, you may not be able to recognize the difference between the previous one and this one. That is why we take some time to draw, okay, as neatly as possible. We also try to maintain the original axis, because axis won't change. So this is over. Now we are ready to do the another rotation, namely the x-axis rotation, which was the first rotation. But this time we have to do in an anti-clockwise direction. You remember theta 1 equal to 90 degree. That was done in the anti-clockwise direction. So the direction also I will specify now. So if you are going to do the anti-clockwise direction along the x-axis, now the horizontal matchbox has to now become vertical one. So that is the idea. Now I am trying to draw the vertical version of that. No, something it's not looking good. I'll erase that portion. Okay, looking okay. Now let us fix the origin and then put the x-axis first. Okay, that will be the x-axis. Then let us say that you are going to draw the z-axis vertically up, and then okay, almost final. Now this is our final configuration. Now you'll have to compare this final configuration with the previous final configuration that was above in the white color drawing. That is why all the time we have taken. Okay, now this is the current version that you have with the final configuration due to theta 2 plus theta 1. So earlier what was there, I'll write down in white color, due to theta 1 plus theta 2. So you see the difference, that was 1 plus 2, this is 2 plus 1. So that is why you have to see the attention and then look at the appearance. Earlier it was looking like horizontal box. Now you see this. Once again, I'll put the round here. Due to theta 1 plus theta 2 is white color. Due to theta 2 plus theta 1 is this yellow color. So their appearance is different. Okay. So that was a horizontal lying matchbox, and this was a vertically lying matchbox. So our conclusion is that there is a conclusion. That's what I am trying to write down. The conclusion is that if you perform, or if you reverse the order of angle, if you are reversing the rotation angles, then we will not get the same result. There is a conclusion. I will write down that from the appearance of the final configurations. Okay, only from final configuration you write this, so that's why I'm writing. From the appearance of the final configurations, we can say that in the case of the 3D rotations, theta 1 plus theta 2, okay, in the case of 3D finite rotations, that is better to write. What is our conclusion is theta 1 plus theta 2 that you have here cannot be equal to theta 2 plus theta 1. And remember, theta 1, theta 2 all are vector quantities. We are supposed to be. The question is that we don't know whether it is vector or not, right? That's what we are saying. Vector means addition rule should be obeyed. Okay, now addition rule is not obeyed. That is what I am trying to say. So our conclusion is that vector addition is not satisfied, so we reject the option. So, but at the same time, now I'll make a conclusion saying that if you are going to repeat the experiment with a smaller angle like 0.1 degree, then the vector addition will be obeyed. So that is what is the thing that I would like to make. This particular experiment where you rotation about 0.1 degree is something that you can imagine and try. Okay, whether you are going to draw it or not, it doesn't matter. It is easy to now verify once this is clear that if you are going to rotate something like anything less than 1 degree, because practically anything less than 1 degree works nicely. So whenever you rotate in angles of less than 1 degree, then it will be obeyed. So finite rotation means not equal to, infinitesimal rotation means it is equal to. So this is our conclusion. The important conclusion is this. So let me put a box here and say that the conclusion is important. So okay, now the conclusions are very clear that 3-dimensional infinitesimal rotations are vector quantities, and therefore we can define what is a very important conclusion is that because of this experiment, our conclusion is that omega, which is an angular velocity, is a vector quantity. That is the conclusion now. Omega is a vector quantity you studied from school, but now we are giving the proof, right? Omega, which is an angular velocity, is a vector quantity because of what reason? That is what we have spent this 1 hour. It is a vector quantity because of infinitesimal rotation. If we were doing the finite rotation, then it cannot be vector. Then the story would have been, mathematics is going to be something different. We can't have vector algebra. Okay, so that is where I have written the statement fortunate. We are fortunate enough to get to enjoy the properties of the vector as long as our angles of rotations are going to be infinitesimally small. That means d theta by dt, when you are going to perform that, the limit comes into picture, no? Limit of the denominator tending to 0. That definition is the one that is going to save our life. And our conclusion is angular velocity in the definition of a rigid body is going to be vector quantity. So with that conclusion, today we will stop, and in the next class we will see how to define linear momentum and angular momentum of a rigid body.